Welcome to our podcast on thermochemistry. You can see that right up here. That's the topic of this discussion. And thermochemistry is a very big portion of the chem curricula and advanced chemistry. And we're going to spend a little time looking over this stuff. But for the most part, there's many things about thermochem that you will already know. So let's just look at this first definition of energy. Now, we've talked about energy all year long, and here's our simple definition from our text: the capacity to do work or cause change. All right. Now, for chemists like us, this is really where energy plays a role in causing change. Doing work, that's a little more of a physics thing. All right, and that has to do with moving an object over a distance. So we don't really talk about work so much in our level of chemistry. We really focus on this causing change. So let's think about the changes we've seen this year. Well, we know about these two, physical changes and chemical changes, right? And those only happen when you get some kind of change in energy. Energy either going in or energy going out. And so if you think about some of the changes we've had, here's something that's often, this one right here, change of state, right? Often people think that that's some kind of chemical change, but it's not really a chemical change. When by the way, for those of you that wonder, what am I talking about? That's like a solid going to a liquid and even going to a gas, right? Well, that can only happen with a change in energy. So if you think about, I've got some ice, right? And how do I make it go to a liquid? I've got to heat it up. Maybe I'll use this flame from way down here and I'll heat it up. And then if I want liquid go to a gas, in other words, I want to boil some water, right? I've got to add some more energy. And so changes of state and of course all the chemical changes, stuff that we used to deal with, that doesn't happen unless you have some kind of change in energy. Now, when we talk about a change in energy, it's usually being absorbed or it's being given off. So let's go over two new terms. And you've probably heard these somewhere along in your science curriculum. But this first one is an endothermic reaction. Now, endo means in. And so an endothermic reaction is when heat is absorbed. And what's really interesting about this, and I'll do a demo for you, when heat is absorbed, the substance gets cold. And that seems counterintuitive because, like, wait, heat is going into a substance. How in the world can it get cold? Okay, but that's the way it works. That heat is actually going in to the substance to be used to do some rearrangement of the molecules, and that requires energy. And so energy is being given off. So, pardon me, energy is being absorbed. The other one, the one that's a little more, well, a lot more common, and the one that people like to see, because most of you guys like explosions, is our exothermic reaction. And that's where heat is being released. And you can think of multiple experiments this year where you felt a temperature increase. And so that was an exothermic reaction. Of course, all the explosions you've seen and a few of the examples of fire you've seen, those are all exothermic reactions. One of the best is this one right here called thermite, and that's where you make basically molten iron. And if you actually spend a little time with me next year in AP, we'll do that at the end of the year. Another common example of an endothermic, and I should have mentioned this before, is this one right here. Okay, a cold pack. Maybe some of you athletes have sprained your ankle on a field, and the trainer grabs this bag and they break it open. They break it inside here, and all of a sudden it's an instant cold. Well, they call it compress, but it's an instant cold pack. And so that's just a reaction where heat is absorbed and it gets cold. All right? Pretty easy stuff, right? Now, this all plays an important role with heat being absorbed and all that, but one thing to remember is the law of conservation of energy must be followed. Now, you guys this year have seen the law of conservation of mass. And it's essentially the same thing, except we're switching the word energy with mass. You can't create it or destroy it. You can only transfer it. And transferring of energy is what you guys see all the time in life. We could think of a lot of examples. I've got a few on the next slide, so let's look at this. So here's a transfer of energy. That's energy being transferred from between systems. So you could think of it as, let me pull this out here. So you can, well, let's see, I'm stumbling here. Let me try and draw a picture. Let's imagine I have this cup of water and it's steaming. Okay, there's my fine artwork. Okay, it's steaming, right? Now the energy is transferring from the cup to the surroundings. And that's what this first bullet is. But let's talk about this because this is something a little more everyday life kind of stuff. Transform from one form to another. So imagine you go ahead and you walk in your room and you turn on a light bulb. And here's my amazing diagram of light bulb right here. You turn on a light bulb, right? Well, what causes the light bulb to light? Well, as you guys know, you have electricity, right? Electricity goes into the light bulb, and now it gets transformed into two other types of energy. One, light energy. You guys remember our chapter on light. And then the other one is heat. But look at this, these two numbers here, all right? This is why light bulbs, incandescent light bulbs, are going bye-bye, all right? Because most of the energy is used as heat. And as you guys know, we don't use light bulbs to heat, we use light bulbs to light. That's why compact fluorescents are becoming the norm. But if you have something like an easy bake oven, right? Some of you might know it, about that, easy bake oven. Well then, light bulbs are fantastic because they can make little brownies and cookies and all those kind of things. But light bulbs are just hugely inefficient for making light, and that's why everything's going into compact fluorescence. Okay? Let's see what I got here. Chemical energy to mechanical energy. All right. So some of you are owners of cars, and in our gas tank in here, we've got gasoline, right? We've got gas, right? Now, you step on the gas, and who knows how it works. It's almost magical to me. But somehow the gas goes in here, and in the engine, it gets converted into heat and mechanical energy. The mechanical energy causes the wheels to turn, and the car moves forward, right? And so there's energy, again, being converted. Right here in the gas, it's the form of chemical energy. And in the instance of moving, it's mechanical energy. And if you've ever felt an engine, you know there is some heat coming off that. And that's why we can turn on the heater, because that heat's coming right from the engine. So there's energy being transferred. Now let's say you're driving and you're texting, oh my goodness, and you didn't notice up here we had a stoplight, right? And you're texting and driving, oh my gosh, and you crash into this other car right here. Well, what's going on there? Well, that energy of the car is going to cause this car to lurch forward, all right? Believe it or not, if we could measure this crash site right here, we could detect a heat increase because some of that energy would be converted into heat energy, all right? Now, let's say you're driving your car, this nice one right here, and you park it near a construction site, and you're not paying attention. And unfortunately, there's a large ball up here, and somehow there's this string is frayed. Okay, you walk away, and right here we have this ball that has a lot of potential energy, and by potential energy we mean it can move, all right, or it's stored energy, depending on the system. Well, as the fray happens, and the string breaks, the ball starts to fall right towards your awesome car. All right? And all this potential energy is converted to kinetic energy, which is a word we've used, and you guys will definitely use it in physics next year. But that kinetic energy is the energy of motion. So the ball's moving, and then it's going to transfer into here, and we're going to have some heat energy, mechanical energy, and all that kind of stuff. So the whole idea about this is that energy can definitely be transferred, and it happens all the time in real life, right? And so the energy of motion, we've talked about molecules moving, especially with our gas laws. That's kinetic energy, and the energy of position is potential energy. So far, so good, right? Well, let's move on a little bit more, because this energy that we deal with a lot in class is heat. And the simple definition for heat energy is it's the energy transferred between objects that are at different temperatures. Now, where have you experienced that in real life? Well, let's say we actually have a sunny day here, like we've had a few, right? And you're laying out on a towel, and the sun's beating down on you. Your skin will pick up that heat, and you will eventually get warm. or it's a cold winter day and you're a little chilled and you stand by this very old radiator, which we used to have in my dorms when I was in college, and the heat that's being given off is transferred to your fingers. Or think of a car. Right. Try not to laugh at my amazing drawing of a car. Oh boy, that is horrible. I apologize to all you artists out there. Okay, and then I go to touch the car door. Oh, here we go. This is going to be impressive. Here's me. I go to touch the door. Here's my long fingers touching the door handle, right? And the door handle feels really, really cold because it's wintertime. Well, the energy is going from my hand to the car. And the way that energy transfers is from warm things to cold things. Okay? And so in this instant right here, I'm warm, car's cold, energy leaves my hand, and so I feel cold. It's not that the car is cold, which it is, of course, but it's that it's sucking the heat right from your fingers. It's kind of an interesting little thing to think about. All right? And so all the kind of temperature changes that you see or heat changes you see are based on this principle of warm air or warm going to cool. That's the direction of the heat exchange. All right? You can think of any example where you're colder than the surrounding temperatures, you'll feel warm. Think about if you jump in a river. You're pretty warm, river's cold. Where's that heat go? It goes into the river. And that's why people who fall into rivers, if it's super cold, they can't survive very long. Okay? So far, so good. All right, I'm going to bring this to a close. This is a nice short podcast, just a real good intro on energy. And what we're going to do next is we're going to talk about this part right here, what kind of temperature scales we use to measure heat energy. If you have any questions on this, like always, just ask me. See you next time.